Okay, we're back. Now we're going to try to model in MATLAB the simple I model. So remember, we're working with the SEIR model eventually, but we just want to look at what happens when the only state variable that matters is I. So let me pull up my MATLAB screen and then we will be able to code along. Okay, so I gave you some suggestions of how you might do the code along. If you're limited to one computer, ideally you'll have a phone or that you can see clearly, or an iPad or something that you can, where you can have two screens going, one to watch this video and the other to code along. So as I code along, I'm going to assume that you are able to type the code as I talk about it, but then at the end, I will scroll through the whole code in sections so that you could take screenshots if you need to, if you weren't able to code along as we did it. Okay, so let's begin. First of all, it's good to be organized. So you want a folder that's going to be useful here. So I have a lot of different physics projects. Let me just start another one with a new folder. This will be our epidemic modeling folder. Okay, so you may want to have a new folder. Whoops, I need to go back up a level, find that epidemic modeling folder. Here it is. Should be able to open that. You can see there's nothing in it. Okay, so now I'm going to open a new document to begin coding. All right, so remember, this is our, we'll call it the I model. Let me make this I, and I'll call it I underscore model. And then let's write a comment. This model for the spread of a disease is only dependent on the state variable I. In other words, the infected, the amount of people who are infected will determine the rate at which people become infected, just like we had in our little formula. All right, so now that I have that, let me save this. So let's save as, let's call it the I underscore model. And save that. I hope it takes the name. Yes, it does like that name. And so there we have it saved as we go. So as always, we want to set up our skeleton for our code. So we will set our parameters. We're going to have a section where we initialize some vectors. We will have a section where we will do calculations. And then we'll have a section where we plot the results. So we'll just call that the plots section. All right, so those are sections of the code. So setting parameters, what things mattered in the code, okay? Well, the state variable I mattered, but we'll call it I0 matters. Let's start with 10 infected people, all right? So this is the initial number of infected people. Shorten it as initial number of infected, all right. Other things that we need to parameterize would be what is the A value. So let's make the A value let's go 0.25. And we're going to make our time period weeks, okay? So this is the coefficient coefficient in, call that weeks raised to the -1. Okay, so it's per week, so 0.25 per week. So remember what that means. Each infected person could infect a quarter of another person each week. So this is going to grow fairly slowly at first. So we'll keep it there. All right. We probably want to have T max because we're going to graph this. Let's say that we'll make that 10. So in terms of commenting that, that means the this will be the number of weeks. Okay, so you don't need units on that because it's clearly weeks. And let's also put an I max a while in. Okay, so I max. If we were looking at New Jersey, that would be, there are 9 million people in New Jersey. So it wouldn't be reasonable to just continue forever. Let's just cap it at, remember we need to have I always being a small percentage of the population in this model. So let's cap it at I, we'll make it 1 million people. Okay, so that would be a large percentage of the New Jersey population, but for now I'll just cap it there. So comment the max number infected graph. Okay, so we'll run off the graph if we go over 1 million people. Okay, I think that does it for parameters. So let's keep going. So remember, these are the things that we'll be able to change. We'll be able to change the initial number of people infected. We'll be able to change how the rate at which the infections can spread with that A value. And we obviously could look at more weeks. And we could also change the cap on the number of people who could be infected. Okay, so now what we need to do is initialize some vectors, okay? We'll need some time. Time will equal, let's go from 0 out to the maximum number of weeks, but let's do this, let's do a time step of 0.1, so tenths of weeks. So that's a little bit less than a day all the way. Actually, let's make that smaller. Let's get more data in there. So let's go 0.01 all the way out to T max. Okay, so we'll take a lot of little steps. So we'll have a nice smooth curve that way. All right, and we need to figure out a, we're going to want to plot the amount of infections. So that will be our I variable. Now we don't know what it's going to be yet. We're going to calculate this in a time-stepping manner. So we're simply going to, let's first figure out how many time steps there are. Let's call that NT. That will be the length of T. So that will give me the number of time steps. So let me put some comments on these. This is the time vector. This will be the number of time steps. That'll be useful as we go to plot. So, and also, we're going to want to have I equal, let's start with there being zeros in all of those time slots. So we're going to have zeros in an array that is one row and the number of time steps of columns. So that will just give me a 0 value at every time for the number that are infected, right? We could also make the first one equal to I0. Whoops, not I0, I0. So we're setting the first value. Okay, so this will be the infection vector. So right now, no one's infected. And then in the next step, in the first time, which will be time 0, but it'll be the first element in that vector, we are setting initial infection value. We need some people, we need an amount of people who are infected so that future people can in fact get infected. All right, so now we're ready to do our calculations. And this is a simple time step loop. All right. So we already have the first number of people who are infected. So we need to create a little loop, simple loop for IT equals 1 out to, we need to go 1 out to NT minus 1. Okay, so that's what we're going to have. We're going to have a loop. I'll put an end to the loop just so we get rid of the red box. Okay, and we need to figure out how to recalculate the I values as we go along. Okay, so remember, I'm just going to call this DI. DI is going to equal A times, so that's really di dt, but I'm just going to call it di, the amount that I is going to change, is going to be A times the I value. All right, so that's the amount of change. Remember our differential equation, that di dt is equal to A times I. So the amount of change of I should be given by that. Let me just pause and get my thoughts together. Okay, so I think the best way to think of this number is kind of like the calculations we had done in the video. This is the rate of change per week, right? So if we take A times I, so if you consider there were 10 infections and A is 0.25, there'll be 2.5 more people should be infected at the end of the week. Now, we're not going to, our time steps aren't a week long, they're much shorter than that. So what we need to do now is say I of IT plus 1. We already know what I of 1 is. So the first time through the loop, we have to calculate I of 2, which would be I of IT plus 1. Which is also why we're only going out to NT minus 1, because we don't want to run over the top of the loop. So it's going to equal the previous I value. So obviously you already had people infected, but we need to add on DI times the size of the time step. Okay, so I'm going to call that DT. Now I just realized we don't have a DT value. Actually, we do. We made a 0.01. Okay, so right now DT is 0.01. It's probably not a very flexible way to do this. So we probably want to define a DT up in our parameter, 0.01, and this will be the size of time step in weeks. And so you can see when we did the, when we made our time vector, we probably should have stepped by DT. So it allows us to change the precision. 0.01 is a good number to use, but it will allow us to change the precision. It also makes it a little bit more obvious what we're going to do here. Okay, so you could sort of think of the DI as if it's an acceleration, and then we're multiplying it. Whoops, there should not be a dot there. Okay, and we're going to multiply it times the amount of time for which we're accelerating, and that will add on to the amount we already had. Better yet, think of it as a velocity. So this very much, don't write this in the code, but this is very much like V, the next V. Do not copy this line of code. I'm just putting it in there to model it. We could find the next velocity, or better yet, the next position. Let's go with X. If I want to find the next position, I would take the previous position and add V of IT times dt, and this would have given me the next position, because a velocity times a little time step will give me a little bit of position to add on to what we already had. That's exactly what we're doing here. DI is the amount of change that we would have if we did it for a full week. we need to multiply that times the amount of time, which is a small fraction of a week, and that will give us the new cases, the new infections, and we'll add that onto the old number of infections to get a new total. So let me get rid of that line of code because we're not working with position anymore. But that's how we would have done time steps for position. So this should now calculate what all of the new I values are. Okay, so now I believe we are ready to plot the results. So see how little code is actually needed. Right? Most of the code was choosing our parameters, setting up our vectors, and a loop, a for loop with just 2 lines of code in it can tell us how many infections we'll have in the next week. I'm sorry, in the next time step, which is a small fraction of a week. So now we're ready to plot the graph. So we just have to plot T versus I. For now, let's just do that. We're going to make it more sophisticated in a moment, but let me run this. Okay, and I have an error, which is to be expected. Let's see, you should always expect that you're going to have some errors when you go to do this. So in assignment, A, D, the number of elements in A must be, okay, so line 22 has a problem. So I of IT plus 1 must equal I plus I of MT times D of I times T. Let me pause the video and sort out this problem. All right, there's just a simple mistake here, which I figured out. We had a problem. It's actually, the problem is in line 21. I was thinking of the formula mathematically, and I said A times I. This is telling me that the rate of change of infections, you can kind of think of that like a velocity for the infections, is A times all of the I's. I don't want to multiply it times all of the I's. I want to multiply it times the I that we're working with. Okay, so the particular I of this loop. So for the first time through the loop, I need to take A times I1, and then I can find in line 22, I2 can be found from I1 plus the rate of change times the amount of time for the change. So I believe that will now work. Let me try running it again. And yes, it did work. I don't know if you can see the new figure window, so I'm going to dock that. So you can definitely see the figure now. All right, and it looks like we have exponential growth. All right. Obviously, we want to change a few things about this. So I'm going to require that to be a blue line. I want to thicken it up so it's a little easier to see on the screen. So here's a way to make a line thicker. You use line width. Notice there's a capital on the W of width because 2 words have been mashed together. So that's a MATLAB convention. Let's make the line width 2. And I'll run it again. So we get a much clearer line when the line width is 2. There are a lot of other things we might want to do. So we will probably want to have an axis command. We want our axis. Remember, we usually do xmin to xmax and ymin to ymax. But it's time on our horizontal axis. So I will go from 0 up to T max on the horizontal axis. And for the vertical axis, obviously the infections never go below 0. So I'll start that at 0 and we'll go up to that value Y max that we had predetermined. All right. So that's my axis command. Let's see what that does when we run it. It does not like this. Okay, let's see, what does it not like? 0 to T max, 0, Y max. And let's see what kind of error it gave me. Oh, it's not Y max, it's I max. Okay, so the vertical axis is infections, so that should be I max. And I'm doing a good job of demonstrating how you have to pick your way through the code. Okay, now that is great, except it looks like it barely grew. Okay, because we made I max 1,000,000 infections, and with my infection rate, the coefficient of being 0.25, the infection rate's really, really small. Let's change that to a 2. and see if we'll notice anything happen in 10 weeks. Wow, so changing that to a 2, we went right off the scale. Okay, so 0.25, we barely ever grew. And as soon as I made that a 2, I went off of the scale. So let's make that maybe a 0.75, and whoops, A equals 0.75. Oh, my number lock isn't on. There we go, and see what that does. Okay, so you can see just it barely moved at the end. So if I want to see what happens, I can just lower I max, so my scale is easier to read. So instead of going to 1,000,000, I'll go to 100,000. And we can see that it's starting to tick up at the end. 100,000 might be too much, so I'll go to 50,000, which in scientific notation is 5 times 10 to the 4th. We're starting to see it. Maybe if I had gone to 20,000 instead, that would be a good number. Okay, so I can change the parameters, okay? Now, what you can see here that's kind of interesting is starting at time 0 with the 10 infections, we barely see the infection rate going up until we get to about week 5. About halfway through, we can begin to see the growth in this. Because the exponential growth starts out very slowly and gets bigger as we go. And I did forget to put a semicolon there when I put in the new number. So that's better there. Okay, so we can see our figure now. It's working, so I probably don't need to see the command window so much. Let's make our graph look a little bit nicer. I always like to put grid lines in, grid on. I like putting the little lines in, so I often put grid minor. All right, so if we put grid on and grid minor, we get a little bit of a grid in there. It may be hard for you to see on your screen, but the grid lines are there. Continuing on, we want to label our axes, X label. So what's on the X-axis? It is time measured in weeks. So weeks of time. So if I put that in, I'm going to have a Y label. Number infected. And I probably want to put a title on of number of infections versus time. There's my title. Now feel free to pause as you're doing this if you have to catch up in the code, but there's my title. And if I do that, what did it not like? Didn't like my title. Oh, because title should not be a capitalized T. The command for putting a title in has a lowercase t. So there we go. We have the number of infections versus time showing up. This looks like we would want it to look. We can see right now I have A equaling 0.75 with an initial value of 10. If I just tick this up to, let's just make it from 0.75, let's make it 0.80. And we can see if we run this again, we shoot off of the top, okay? So a small change in A greatly changes the way this infection is going to play out, okay? Now, this is not a bad model for how a virus could spread at the beginning, okay? Now, the only problem is somebody's probably not going to be infected over 10 weeks. So some of these initial people who get infected, well, they'll give the infection to others. They probably will drop out of the infected pool. So this is exaggerating the results, okay? But the assumption that we have a low percentage of our population infected is a really good one. Notice we capped this at 20,000 people. If we're simply looking at New Jersey, 20,000 people out of 9 million isn't that many. Now, another limiting factor of the model is if we get infections, they tend to happen in clusters. Okay, so we assume that infected people don't bump into other infected people later, that they keep infecting new people. But you could have a cluster of people and you could quarantine just that cluster so that they can only sort of infect people within a much smaller cluster. But that breaks down this model because this model assumes that every infected person has many susceptible people available to infect in the next time period. Okay, so now that you have this model, you can easily change the numbers around and see what happens. This is exponential growth. You can see that we get small growth in the beginning and it just rapidly takes off as we get to about the 5-week mark. So this is a good model for exponential growth. So on your homework, I may have you, use this model and just evaluate what happens for a couple cases with different initial values and different coefficients for the infection. So let me stop this video and you should be ready to do your homework at this point.